Hello friends, welcome to this live session on our ongoing MOOCs course Fundamentals of Nuclear Power Generation. In this live session I am supposed to be available for quite some time with you, and if you have any query I am going to respond to that during today's session. Of course there are already quite a few pending queries in the portal. I am also going to respond to that. While I could have responded that in writing in the portal itself, but some of the queries sometimes is difficult to explain just with the help of a few written words, and so I thought about talking about the same, discussing the same during the live session itself. Yeah, Himanshu, good afternoon to you. If you have any query, you can write here. I am going to respond to the pending queries, and then I am going to take up whatever questions you have. Yes. Yes. So, in this live session, the first question that I am taking up, that is a question where it was asked according to the Rutherford Bohr model of atom. There's the nucleus in the center and electrons orbit around that. Definitely, that is the correct idea of the Rutherford Bohr model of atom, which is assumed to be somewhat similar to the solar system. There is a heavy nucleus comprising of protons and neutrons at the center, and electrons are orbiting around that in circular or semicircular elliptical kind of orbits. Now, is there a specific number of electrons such as that of protons or neutrons in various elements? I read somewhere that the electrons exist around the nucleus in the form of cloud, and their count is not well defined. How well do we know about the behavior of electrons? Is there an aspect of nuclear characteristics of an element that is affected by electrons, like how the mass, atomic numbers affect nuclear characteristics? Thanks. Now, there are two parts of the question. Firstly, regarding the number of electrons around the nucleus. You are partially correct. Rutherford Bohr model was the first and very preliminary model of atomic structure. There are several other development on that, like the Schrodinger model, etc., where they talk about instead of electrons exiting in fixed orbits, there is an electron cloud around the nucleus, and the electron can stay anywhere inside the cloud, and that can move over the entire cloud, and the wavelength of those electrons is equal to the diameter of the entire atom itself. However, the number of electrons can't be separate, because you know very well that the protons are positively charged, and now is there is any means suppose if we are talking about any particular isotope where there is, say, let me talk about, say, oxygen, you know, has 8 protons in the nucleus. Now there has to be 8 number of electrons are in the orbits or in that electron cloud, otherwise it can't be electrically neutral. So as long as you are talking about an electrically neutral atom or electrically neutral isotope, then the number of electrons and number of protons has to be equal. Only difference is that the protons stay inside the nucleus and electrons are staying inside in the electron cloud, but the number has to be equal to each other. It's If the number of electrons are different, then of course it can't be electrically neutral. It will form an atom. Like if the number of electrons is more than the number of protons, somehow if one electron gets added to this, then it will become negatively charged. If the electrons are removed from the orbits, then it will become positively charged. But for an electrically neutral atom, number of electrons has to be equal to each other. Yeah, Mahesh, I can see you have written good afternoon, so the same to you. If you have any query, you can write. Now coming back to the same question, there is a second part also. Is there an aspect of nuclear characteristic of an element that is affected by electrons? Truly speaking, no. In this particular course, or whenever you are talking about nuclear energy or nuclear power generation, we are concerned only about the nucleus, because whatever changes that are happening, that is happening inside the nucleus only. During any nuclear reaction, it is the nucleons, that is the constituents of the nucleus, that participate. Electrons have no role there, and therefore the nuclear characteristics are not at all affected by the presence of electrons. So I hope I am clear with this. I am moving to the second question. In the second question, I was asked regarding a particular example where I talked about the hydrogen energy. I think it was in the second lecture. So when you are talking about the binding energy of hydrogen, there we have 1H1, that is the general isotope of hydrogen or protium, which is nothing but a proton that absorbs one neutron and forms 1H2. Now, if we want to calculate the binding energy associated with this deuterium, then we need to know the atomic mass, or I should say the nuclear mass of all the involved isotopes. Here all the data I am taking is from this particular website, that's why I have put it here. You can just use the same thing in the hyperphysics.com or hyperphysics.edu. You can get the periodic table, and once you click on any particular element of the periodic table, it will show all possible isotopes and their characteristics of that particular element. And that's where I am taking all the data, because this is a very reliable source to have. Now we know that protium is just a proton only, and so the mass of one proton is 1.007835 U approximately, and it is reacting with a neutron whose mass is 1.008665 mu. This is what we have on the product side. On the reactant side, we have deuterium from that same database. Its mass is 2.014 mu. So this is the mass, say, m1, this is the mass 2, then the corresponding mass defect delta m is m1 minus m2, and if you just calculate this, we are going to have 0.0025 amu, and hence the corresponding binding energy will be this energy corresponding to this mass defect. So we have to multiply this with 931, so 0.0025 multiplied by 931 is equal to 2.3275 MeV. This is how we can calculate the binding energy associated with any nuclear reaction. I hope you got the answer now. And if your interest is to calculate the binding energy per nucleon, then you have to divide this by the number of nucleon present in the deuterium. In this case, of course, it is 2, 1 proton and 1 neutron. So if you divide this 2.3275 MeV by 2, you are going to get binding energy per nucleon. So I move to the next one. In this question, is the concept of mass defect applicable for chemical reaction? As far as I knew, in a chemical reaction, the electrons get rearranged due to the reaction with changed orbit location. This produces the energy in an exothermic reaction and absorbs energy in an endothermic reaction. There can be small mass defect, but that is not the sole reason for liberating absorbing energy. Please elaborate if my understanding is wrong. What you are saying that is partially correct. The concept of mass defect is applicable for chemical reactions as well. Only difference is that the amount of mass defect and corresponding release of energy or conversion of mass to energy is much smaller when you are talking about a chemical reaction. Definitely during a chemical reaction, it is the electrons which gets rearranged due to the and accordingly we have the production of different kinds of compounds. But the elements, that is the nucleus, they are not at all affected. However, when we are having this new compound formation, there will be still small amount of mass defect between the product and reactant side, and that amount of mass defect always gets converted to energy, and that's where we get the exothermic energy, or sometimes if the mass of the product is more, then we have the endothermic reaction. So whatever energy interaction we are talking about during chemical reaction, that actually also comes from the mass defect, but the magnitude of that is generally so small that it hardly matters how much difference in mass is present between the products and the reactants. So it is the liberation or absorption of energy, rather the mass defect itself is the reason behind this liberation or absorption energy even during the chemical reaction, but the magnitude is much smaller. Generally the magnitude, you can see if we compare with equal amount of fuel, if we compare the energy released during a chemical reaction and energy released during a nuclear reaction, there can be about 5-6 order difference or even more. So the mass defect is still present during chemical reaction, but it is extremely small. But you are very correct. It is because of the rearrangement of the electrons only that we have the formation of new compounds. In the nucleus side, there is no rearrangement, but there will be still small amount of mass defect within the product and reactant nuclei. So I move to the next one. Mahesh, I shall be coming back to your query after I respond to all these questions. So number 4 is, sir, my question is that is it for each and every element there is a relative mass defect in it to the actual mass we calculate? Yes, the mass defect always has to be there. Remember what is the constituent of the nucleus? In the nucleus you have protons and neutrons. Now protons are positively charged whereas neutrons are electrically neutral. So particularly when you are talking about a slightly heavier isotope, then there are lots of protons with the same electrical charge, they are staying within a very small volume, and so there has to be a very strong repulsive force generated because of this because of this electronic interaction. Now there has to be then some kind of opposing force which will bind all these protons together inside the nucleus. One possible kind of force is gravitational force, but I think it was demonstrated during one of the lectures that the magnitude, or rather the order of the gravitational force, is way too small compared to this electronic repulsion force or electric repulsion force. So we need to have some other kind of force which is commonly called the nuclear force, and that nuclear force comes from this binding energy which actually is originated from the mass defect. So mass defect is always there. Whenever we are talking about any isotope, we are talking about any nucleus, the mass of the nucleus itself will be always slightly lesser than the combined mass of all the protons and neutrons which are constituting this particular nucleus. And this defect or this differences mass is getting converted to binding energy, and that is that nuclear force, which is a very strong force but generally short lived or short ranged one, that it is a binding energy which is binding all the nucleus together. However, as I mentioned, it is short ranged one, so it is generally not felt too much outside the nucleus itself. So the mass defect is always there. Now I move to the question number 5. After the collision of neutron with a nucleus, how are we so sure that the trajectory of the nucleus and neutron will be strictly 180 degree? If a neutron hit nucleus by an angle, this assumption would not be valid. And definitely we are never assuming that there will be always 180 degree deflection of the neutron. The deflection can be by any angle, and the neutron can also hit nucleus by any angle. While doing the analysis, we have generally calculated the logarithmic energy decrement, or rather the relation of energy decrement for a neutron with a collision in terms of just any random angle theta. The neutron can strike the nucleus from any possible direction, and accordingly, depending upon the cross section of nucleus, also may get deflected by any possible angle. And therefore, when you are trying to calculate the logarithmic energy decrement, then we have to consider the entire spectrum, and we have to integrate it over the all possible directions on which the neutron can get deflected. So it is not mandatory to be 180 degree, but 180 degree is one of the simplest cases. Actually 0 degree, there is no deflection at all, and 180 degree, these are the two limiting cases, and the neutron can get deflected by any angle including these two. The next question corresponds to if a neutron collide head on with a nucleus and loses its all the energy and comes at rest, as nucleus mass is quite high compared to neutron, it is at rest too. So COM angle will be 0 and energy lost won't be 0. I am not sure exactly what you are trying to mean, but if the neutron has come to rest, then it has lost all its kinetic energy. So it has lost its entire energy, and energy lost definitely is not 0, because rather it has lost entire of its energy. So energy lost is equal to its own kinetic energy with which the neutron is coming to strike the nucleus. It is theoretically possible, but practically don't happen too much. It is only when the nucleus absorbs the neutron itself, then only there is no deflection possible. Otherwise the neutron will always get deflected by some angle between 0 to 180 degree. and so there will be always some kind of loss in energy. Only when the neutron comes completely to rest, which actually is that 0 degree that we are talking about, that is the entire of its energy will be lost. The seventh question that I have, as per the instructor, normal water is a good moderator as it requires less number of collisions to thermalize the neutron. But okay, you are referring to assignment 3, question number 6 says that heavy water is a good moderator. Is the question correct? If yes, please provide me with necessary content. Yeah, the question and the answer both are correct. Definitely, the normal water or ordinary water is a very good moderator, and if you just look at their number of collisions required to thermalize, then light water definitely takes less number of collisions. But while judging a material whether that is a good moderator or not, we have to use the term moderating ratio. It was taught during the lectures, because the slowing down of the neutron alone is not sufficient. We also have to ensure that the moderator doesn't absorb too much neutron. So the moderating ratio is defined as logarithmic energy decrement multiplied by the scattering cross section divided by the absorption cross section, or we can multiply both numerator and denominator with the nuclei density, and we can write them in terms of their macroscopic cross section notation, sigma s upon sigma a. Now, one of the tables that was presented during the lectures, if you look there, the value of this moderating ratio for normal water is only around 62, whereas that for heavy water is way high, around 4830. That is much larger than normal water, and that's why we call heavy water is a better moderator. From where this difference is coming? If you compare the values of their scattering and absorption cross section, scattering cross section and absorption cross section, okay, absorption cross section is a combination of capture plus fission. Now the materials that we are talking about, for them fission cross section is 0. So absorption and capture cross sections are same. So corresponding to thermal neutron, for ordinary water the scattering cross section is 20, and for heavy water the scattering cross section is 4. So it may seem that okay, actually I am writing for H1 and H2, the two isotopes of hydrogen. So it may seem that it means the deuterium and correspondingly heavy water, which has about 1/5 of the scattering cross section. So ordinary water definitely seems to be a better moderator. But the problem lies with the absorption cross section. For deuterium, the absorption cross section is extremely low, point triple not 3, whereas for ordinary water, or rather ordinary hydrogen isotope, it is 0.2. So it has about 1000 times greater probability of absorbing neutrons, and that's why we consider the ordinary water as an inferior moderator compared to heavy water, and that quantification comes in terms of this moderating ratio. So that's why we mentioned that heavy water is a better moderator. So now these are the questions that were there in the portal. Now I go back to the question of asked by Mahesh. Mahesh, here you are asking, can you elaborate more on how nuclear energy is renewable source of energy as fuel source is limited like uranium or thorium source? Mahesh, you are correct. The sources of nuclear fuels like uranium and thorium, they are definitely limited, like any normal source or like coal, etc. But we can still consider nuclear energy as a renewable or more, I should say, sustainable form of energy, because using nuclear reactions we have the possibility of converting the fissile isotopes. Sorry, we can have the possibility of converting the fertile isotopes to fissile isotopes. Like you know that uranium the natural uranium that we get from mines, 99.3% or more than 99% of that is uranium 238, which is not at all a fissile isotope. The fissile isotope is uranium 235, which is only 0.7%, and so that is that definitely can't participate, or I should say that participates in fission reaction, but that definitely is not an infinite source. But the advantage that we get during any nuclear reaction inside the nuclear reactor, we have both uranium 238 and 235 present. 238 definitely is present in much larger quantity than 235. While 235 participates in fission reaction and gets consumed, uranium 238 also absorbs nitrogen, absorbs the neutron. Its fission cross section is very small, but it has a quite high capture cross section, particularly within the resonance absorption zone. Now, when uranium 238 captures one neutron, it gets converted to uranium 239, which actually is a radioactive isotope, and therefore it undergoes natural radioactive decay. Uranium 239 goes through two steps of beta decay to produce plutonium 239, which actually is a fuel. So uranium 238 can be converted to plutonium 239 and can be used as a fuel. So something which is not a fuel, we are able to convert that to nuclear fuel, and uh, we are able to use that for much longer period. Similarly for thorium, in India we have significant amount of thorium 232. That is probably the largest among the entire world, among all the countries. Thorium 232 is again not a fissile isotope, but it is a fertile isotope. Thorium 232 can absorb the neutron and gets converted to thorium 233, and thorium 233 in two steps of beta decay gets converted to uranium 233, which is a fissile isotope, and so that can participate in fission reaction. So it is possible that we can convert fertile isotopes like uranium 238, thorium 232, plutonium 240, etc. into fissile isotopes and can use them for much longer, and that's why we quite often call the nuclear energy to be a renewable or sustainable form of energy as well, because we can produce the fuel during the nuclear reaction itself. There is another query that I am getting from Manisha. In India, where will be the new nuclear power plant be established in issue zone? Unfortunately, no new nuclear plant is coming anytime sooner. At least not within next 2 3 years. But some of the existing plants that are getting expanded, like the Tarapur plant, which is the oldest station, that got expanded quite a bit. We have expansion in several others also, the Narora plant, the Kakrapar, which is a new plant. They are all getting expanded, but new plants are not coming in immediate future. But you know the reasons, because whenever you are talking about nuclear energy, there is lots of debate about that, lots of apprehension about the use. Though nuclear energy has not led to any significant accident apart from that one incident in Siberia, that is the Chernobyl accident in 1986. Apart from that, there is hardly any nuclear accident that has happened over the entire world. But still, there is lots of apprehensions, lots of public demand or public agitation whenever there is a proposal for setting up a nuclear plant, mostly because of the misconceptions that people have regarding the nuclear energy or the nuclear fuel. But hopefully the situation may improve in future, because while the conventional sources like coal etc are getting depleted, the use of sources like hydropower that almost got saturated, and we are yet to reach the commercial stage with renewable sources like solar or wind. So at some point, of course, the enhanced focus should come back to the nuclear energy, which already is contributing about 10% of the national production, and is likely to contribute even more in years to come, particularly with the generation 4 nuclear reactors coming around 2030. We may see a boost in the nuclear power production. So if you have any further query, you can ask me. I'm available here for some more time, and Then we can wrap up the session if there are no more queries. In the course, I hope whatever I am discussing, you are able to get that. Initial few weeks we are not able to respond properly in the portal, but probably now you have responses of all the queries. There are some queries about revelation of assignments, etc., which we shall be taking care, or we have already taken care of in some of the cases. So don't get worried about that. I have seen there are queries coming where people are talking about not getting marks because of spelling error or use of capital letter and small letter. Don't get too much worried about that. Yeah, it happens with the evaluation software, but we shall take care of that definitely. So if you have any other query, you can ask me. You can see quite a few are available live, so it will be nice to hear from any of you. This course of fundamentals of nuclear power generation, it's a very interesting course, though I have not gone up to that much detail, but here it is possible to go to the most fundamental of physics, the quantum physics or nuclear physics, where you can talk about the configuration of neutrons and protons, and the I concepts of quarks and leptons, baryons and again the leptons, etc. And but of course I have not gone up to that much detail. The concepts like conversion of quarks from one to another, that that is extremely interesting but maybe quite complicated as well, particularly considering this is a first course on nuclear power generation almost for all of you. Okay, I have some other query. One is what's your opinion about use of nuclear energy in rockets that is already under utilization? Nuclear fueled nuclear fuel rockets or nuclear fuel submarines, they are already in use, and people are using either particularly in rockets people are already using nuclear fuel or the solid fuels like hydrogen based fuels, etc. So you can search over internet and you can find some more information about the nuclear power rockets. So Mahesh, if you have any query, because you wrote something and then you deleted, if you have any query you can write to me now again. Because like in a conventional classroom we have the option of having direct interaction, having eye contact, and that is something we all prefer. Being teacher, it is always preferable for us to explain the concepts directly to the audience, have an opportunity of getting their feedback properly, feedback immediately I should say, also clear their doubts at the spot itself. But in this online mode of learning, particularly with these MOOC platforms, with SRM platforms, we are restricted only across the screens, and so only way I can interact with you is once you provide some message here. Okay, I have got the message from Mahesh again. I learned that in PWR type we use parallel flow heat exchanger. Reason is something like ram force. Well, this ram force, this term is new to me. I don't know what it does mean, or is there is. I don't think it has any specific reason or specific significance for nuclear power generation. And PWR not necessarily uses parallel flow heat exchanger. You are correct that counter flow heat exchangers are more efficient than parallel flow, and so there is no rule that PWR has to use parallel flow or counter flow. That always depends upon the ease of installation, sometimes the ease of all the pipings providing, and counter flow heat exchangers are definitely used compared to parallel flow. Probably counter flow heat exchangers are more commonly used than parallel flow, because obviously because of the reason that you have already written, that they are more efficient than parallel flow, theoretically at least. Any other query from anyone? If anyone wants to ask anything, please do that now. Okay, thank you, Mahesh. If you have any other query, you can write in the portal or you can send a mail to me. I shall be happy to respond. So, if other queries are not coming, maybe we can. Okay. Oh, that's a quite philosophical question. How can we aware people from fear of nuclear power generation? That is the focus of offering such a course where we can educate technical people like you about the fundamental procedure behind nuclear power generation. And once you know how the power is generated in the inside the nuclear plant, and also how we utilize that power, what are the precautions that we take about the management of the waste fuel, then naturally people will get rid of this fear. Of course, if we want to get rid of this fear at mass level, we need some support from the government agencies, maybe some kind of drive with some kind of educating drive where scientists can go to the local people and talk with them, maybe show them about some shows about how to or how the energies are generated, etc. But nowadays, as days are going on, nuclear plants are becoming even more and more safer. Like we started with the generation 1 nuclear reactors, and now we are into the generation 3 or 3 plus, and soon we are going to start generation 4. And the major difference across the generations are not the technology of power generation, because that remains the same. Ultimately, there is nuclear fission only, but the major thing that changes is the safety precautions, the protocols that needs to be followed around the nuclear reactor core in order to eliminate all possible options, all possible avenues of any kind of nuclear accidents. So that's something we have to educate to people. I don't know whether it is possible to have in an individual capacity or not, but more and more of students like you know about the fundamentals of nuclear power generation. There is a greater chance that you can also spread the awareness among your neighborhood, within your neighborhood or to your friends, and accordingly can start some kind of chain. So I hope, Manisha, you got my response. It's again, it's a question where we don't have a direct response. It's only the possibilities that we are thinking about. So if any other query from anyone, please. So if queries are not there, maybe we can wrap up this session. Okay, thank you, Manisha. If you have any query, please write in the portal or please write a mail to me. I am available to respond to you. So we shall be meeting again for another live session later on. Thank you very much. Thanks for your participation. Take care.